In this section, we're going to look at rational functions. Now, a rational function is one that is a fraction of polynomials. A rational number is just a number that can be written as a fraction, so that's where the term rational function comes from. All right, so here's kind of the formal definition for it. We have a rational function when you have p of x divided by q of x, where both the p and q are polynomials of some kind. But let's start with the simplest rational function we can, which is one of our toolkit functions. F of x is equal to 1 over x. And let's start by thinking about what's happening here when x equals 0 on the y-axis here. Well, just by looking at this function and our knowledge of domains, we know that this thing has a domain of negative infinity up to 0, but that I'm not allowed to plug 0 in because that would cause me to divide by 0. And so there's my domain. So I know that this graph does not exist at 0. But let's think about what's happening as we get close to it. So you can see right here, if I go to x is equal to a half, then what I'm doing in the function is my y value would be 1 over 1/2, or 1 divided by a half. And we know that when we take 1 divided by a half, we're just going to end up multiplying by the reciprocal of 1/2, and so we get 2. So that puts me up at a y value of 2. But the closer I get to 0, the more extreme it gets, right? So for example, if I go to 1/4, then the y value for 1/4 would be 4. So that puts me even higher. So you can imagine that what's going on here is if I wanted to get really, really close to 0, let's say I wanted to go to 1/1000th, then the y value would be 1000, right? So I'd be way up there. So what we see is that as we get close to 0, one of two things are going to happen. On the right side, we are going to explode up to infinity. And on the left side, we just explode downward to negative infinity as we get close to 0. And then we can also understand what's happening out here when we think about what happens if I plugged in something really extreme way out here. What if x was equal to 100? Well, if x was equal to 100, then y would equal 1 over 100, so really, really close to 0. So as I go off for high x's or for really negative x's, these y values should get closer and closer to 0, or closer and closer to the x-axis. Okay, so this introduces a couple ideas to us. First of all, vertical asymptotes. So a vertical asymptote will occur where the denominator of the function is equal to 0 and the numerator is not 0. So in this particular instance, we would say x equals 0 is our vertical asymptote for 1 over x. And let me skip down to this one here. So it says the line y equals b is a horizontal asymptote if y approaches b as x approaches plus and minus infinity. Well, we saw up here that as x goes to positive infinity and as x goes to negative infinity, y gets close to 0. So what we would say down here is that y equals 0 is our horizontal asymptote, right? It's the horizontal line that the graph seems to approach. And then the one other definition to talk about, but that is not apparent here, is that we have this idea of a hole. So a hole occurs in a graph when a particular input causes both the numerator and denominator to be 0. Okay, so let me give you just an example here, and we'll kind of put this in a different color to really emphasize that this is a different example than here. So what if we had g of x is equal to x plus 2 divided by x times x plus 2? So if I had that, by the algebraic rules we already know, we could cross out these x plus 2's if all I was looking to do would be to simplify, and then I'd get 1 over x. So the idea here is that this graph should look just like the graph 1 over x. But the fact that x plus 2 was here means that I still cannot stick in an x value that makes it 0, and so that would of course be x equals negative 2. So the idea with g of x would be that it would look exactly the same as the graph we already have here, but at x equals negative 2 there would be a hole, because we know we're not allowed to be equal to x equals negative 2 in this function, right? Because this function has a domain of negative infinity up to negative 2, regardless, and then negative 2 to 0. This is the domain regardless of what kind of simplifying you can do. Okay, so that's what happens when you basically get this cancellation on top and bottom, and yet this was still the original function, so we have to kind of honor that, and we place a hole in the graph there. All right, so let's take a look at an example. So we've got r of x is equal to x plus 3 over x squared plus 2x minus 35. So what we want to focus on is, like we did with polynomials, we want to focus on long-run behavior, and we also want to focus on short-run behavior, so really zeros and vertical asymptotes. So let's just kind of go through these one by one. So first of all, in order to find zeros and vertical asymptotes, if we can factor our function, we should. So I can see in the denominator there that this looks like it might factor. So I'll go ahead and do that. So let's see, negative 35, we're looking for things that multiply to make negative 35 and add to make 2. So I'm kind of thinking plus 7 minus 5 looks pretty promising. And so from that factorization, I see there's no canceling that can be done. So the first thing I can note is that in this particular rational function, there are no holes. Because if there were, I would have, like the same factor, x plus 3 and x plus 3 on top and bottom, that I'd be able to cancel, right? So there's no holes here, so we don't have to worry about that. So let's think about zeros. So zeros occur when the numerator equals 0. Okay, not the denominator, but just the numerator. So we would say x plus 3 equals 0. Sorry, I'm going to erase that real quick. So of course we get x is equal to negative 3 as our 0. And I'm not going to immediately put that on the graph because I want to see where all the other important parts of the graph are, so I kind of know how far apart to put my tick marks. All right, so there's zeros. So now let's do vertical asymptotes. So vertical asymptotes, that's where the denominator is 0. So we set x plus 7 equal to 0. That's one way for the denominator to be 0. And also x minus 5 could equal 0. All right, so we have a 0 at x equals negative 3, and then a vertical asymptote at x equals negative 7, and a vertical asymptote at x equals 5. All right, so two other things we want to do now. The first is to think about horizontal asymptotes, right? The long-run behavior. So we want to know for horizontal asymptotes, as x goes to plus or minus infinity, y goes to what? If we can answer that question, then we know what our horizontal asymptote is. So in order to do this, what we're going to do is take our original expression, our original function, x plus 3 over x squared plus 2x minus 35. And what we'll do is multiply the top and bottom by 1 divided by, in this case, x squared. So I'm going to look at the highest power term in the denominator and multiply by 1 over that. And you'll see why we want to do that in a moment. But of course, if I do that, I've got to do it on both the top and the bottom, right, to make it legal. So as I distribute through on the top, I get x over x squared plus 3 over x squared divided by x squared over x squared, oops, sorry about that, plus 2x over x squared minus 35 over x squared. And then I simplify whatever I can. So up here, this is 1 over x. 3 over x squared stays the same. But then I have a 1 here plus a 2 over x minus a 35 over x squared. Now, here's the reason I did this. If I want to plug really, really big numbers in for x, then in this expression, before I multiplied by 1 over x squared, well, let's go back up here. If I plugged a really big number in to x plus to x on top, I would get a really big number. If I plugged a really big number in the bottom, I would get another really big number. So what that means is that it's hard to tell what's happening when you plug big numbers in for x when the function's written like this. But what I've done now is I've just algebraically manipulated it, and I've done it in a way so that I end up with a 1 on the bottom. And the reason I like doing that is because now I'm going to do the same thing I had already written up here. I'm going to let x get really, really big. Okay? And if x gets really, really big, that's going to affect all these terms, but the 1 is going to stay the same. So let's just analyze what is it exactly that happens if we let x go to plus or minus infinity. Okay? If we do that, then imagine plugging a really big number in for x, like 1,000. Would you agree that 1 over 1,000 is pretty close to 0? So what we would say is that this first term, basically, I'm going to use a little arrow here to indicate, let x go to plus or minus infinity, then what's this whole thing going to do? That first term's going to go to 0. The second term's going to go to 0. The 1 is going to stay left alone. This term's going to go to 0. And this term's going to go to 0. And so what that all tells me is that as x goes to plus or minus infinity, y has to go to 0. All right. So that was a lot of work. I'm going to show you a shortcut later, but what that does tell us is that y equals 0 is our horizontal asymptote. And so if I back up to our example here, we also said that y equals 0 was our horizontal asymptote for this problem. So we know that in the long run, on the edges of my graph, our graph should be settling down to the x-axis, just like in this one. Okay, so we're almost there. I'm going to start the process of graphing and then do one other step before we complete the graph. So I'm going to start putting in important things like zeros and vertical asymptotes, and I can kind of get a pretty good sense of where my tick marks should be. So I'll put them about this far apart. 4. Okay, so here's -7, we know that that is a vertical asymptote. So I'm going to go ahead and put in a vertical dashed line. And you're always going to do this, and the only reason it wasn't done on the example of 1 over x is just because that vertical asymptote was right on the y-axis. Okay, so if you're on an axis, you don't actually put the asymptote. And then we're also going to make tick marks over here. And there's 5, so we'll put vertical asymptote there. And then we have a 0 at -3, so that puts us with a 0 right there. Okay. And so the only other piece that I want to do formally here is to also find the y-intercept. And the reason I want to do that is just because it gets me another point to look at and kind of helps me understand about how things are shaped here. So the y-intercept is when x is 0, so we plug 0 in for x, so that's going to be 0 plus 3 divided by 0 squared plus 2 times 0 minus 35, which just gives me -3 over 35. So what does that tell me? That tells me that when I cross the y-axis, I'm at -3/35, which is basically right here. So in other words, from this 0 to this y-intercept, I've barely changed my height at all. And that's really important information, because here's what it tells me. This 0, I know, has to approach asymptotes. Okay, so I know that between this 0 and this negative y-intercept, I'm going to have to be below the x-axis. But because that y-intercept is basically right at 0, I know it's going to kind of have to hug the x-axis. And I also know that because my 0, going back to polynomials, only has multiplicity 1, I have to cut straight through the 0. So I'm going to go up to the positive side here as I go over here. And because of the idea that it doesn't change height very quickly, I'm going to kind of hug this x-axis. But I know eventually that as I get closer and closer to this vertical asymptote, it's got to explode up out of control on the positive side. And as I continue over here, since I'm on the negative side, I know I'm not going to bounce up here, because the only way that I could go to the positive is to have another 0 in here, and I don't have one. So I'm going to stay negative and make sure that I approach my vertical asymptote as I get close to it. So how do we figure out what's happening on the outside of these vertical asymptotes? So let's start over here on the left. There's a couple ways to think about this. One is that if it's positive on one side of the vertical asymptote, then it should switch signs on the other side of the vertical asymptote as long as the factor that's producing that asymptote is only to the first power. And the reason for that is, like, if you plugged in -6, right, which is this x value right here, if you plugged in -6 up here, this factor would give you +1. But if you plug in -8, which is on the other side, this factor switches to being a negative factor because it becomes -1. So overall, this expression would have to flip signs. So you know it's got to flip over here too. Another more concrete way of doing it is just go ahead and put in -8 for x, right? And see how it all shakes out. And so if you put in -8 for x, the top becomes -5. The bottom becomes -1 times -13. And the actual number itself really doesn't matter. But can we all agree here that the answer is negative? And so just doing that one little calculation means you're down below the x-axis. Because there's no other zeros over here, you know it's not going to switch to being positive all of a sudden. So you can say it's definitely down here somewhere. So this one, and you can see it's pretty close to the x-axis, so I'm going to put it up here. And we know as x goes to negative infinity, y should be getting closer and closer to the x-axis. And so we look something like that over there. And a similar logic would say that when I switch sides of the vertical asymptote of 5, I should switch signs here. And again, plug in a number, plug in r of 6, see how it comes out, but it's going to come out positive. And so we've got something like this. And like always, you're responsible to be able to do this without the use of a calculator, but at the same time, check your work on the calculator. That's no problem. So let's take a look at another example here. So like we did on the last example, let's begin by factoring out the top and bottom, if possible. On top, we can see there's some easy factoring to be done, right? There's a common factor in both the top and bottom. In the denominator here, looks kind of promising as a potential situation where we can reverse FOIL. I'm thinking -3 plus 2. I think that'll do the trick. And then up top here, this is a difference of squares, so that can definitely factor as well. So this will be x minus 3 times x plus 3. And x minus 3 times x plus 2. Okay. Now, of course, algebraically, we see we have two identical factors on top and bottom, right? So they can essentially cancel, right? But we got to be a little bit careful about that. So they cancel. Okay. But let's just, by this equal sign, let's make a little note. But x minus 3, or x still cannot equal 3. Okay, even though they kind of disappear in a sense, you still can't allow 3 into your function because it'll still cause you to divide by 0 in this original function. But other than that, right, and actually let's just go ahead and write here. So x equal, let me say it this way. So there is a hole at x equals 3. Okay. But besides that, we really can treat this function as if it looked like this, x plus 3 and x plus 2. Okay, so we can do the rest of our analysis, just that, and then we just got to remember to plug in x is equal to, or plug in a hole at 3 when we make the graph. All right, so let's go through here. Since there's only one factor on top, we can see there's only one 0. So x plus 3 equals 0. So that means x equals negative 3 is a 0. And vertical asymptote, we have x plus 2 equals 0. So x equals negative 2. All right. And then let's do horizontal asymptote, right? So horizontal asymptote, remember the name of the game here is we take our original function, and let's just take the original here, right? Just go back to the very original one. I could use the simplified version, but I'm going to use this because when I'm doing this analysis, I kind of like to have it all multiplied out rather than factored. And the original has it all multiplied out. And so remember what we're doing is we're looking at the bottom, we're saying what's the highest degree term on bottom? Well, that's x squared, so I'm going to multiply by 1 over x squared on top and bottom. Now in the last example I showed a lot of detail work when it comes to simplifying this. I'm going to show a little less here, but just remember we're distributing through both top and bottom. And so in the first term on top, 3x squared divided by x squared is just 3. 1 over x squared times negative 27 is negative 27 over x squared. And then on bottom we have a 1 minus x over x squared is 1 over x when it's simplified, minus 6 over x. Now the key here is that what is it that happens, right? What happens if we let x get really big or really small? So down here I'll say as x goes to plus or minus infinity, what is y going to? Well, this term, when x goes to a really big or really negative number, goes to 0, because you're taking 27 divided by a giant number. Like think a million. 27 divided by a million is pretty close to 0. Same thing as 1 divided by a million is pretty close to 0, right? Oh, and I apologize. I can see somehow I forgot my square on this term here, excuse me. So 6 over x squared, but doesn't change the analysis. We're still heading to 0 there. So y is heading to what? 3 over 1, right? So 3 minus 0 over 1 minus 0 minus 0. Which equals 3. So that all says that y equals 3 is my horizontal asymptote. So just like we have to put dashed lines in when our vertical asymptotes don't align with an axis, we also have to put them in when our horizontal asymptote doesn't align with an axis. So what we'll do here is let's put some tick marks for our y values. All right, so at y equals 3, I'm going to put a horizontal dashed line. We'll put our vertical asymptote here at x equals negative 2. And then we have a 0 at negative 3, right? So that's our 0 is going to be right there. Okay. All right, so we are taking a look at what we've got here. And so what we need to do now is determine kind of where things are at, right? Are they above this horizontal asymptote, below it, or above the x-axis, below it? So remember, like we did last time, it might be nice to go ahead and find the y-intercept, which is easily found just by plugging in 0. So f of 0, and I'm going to use this version because it looks pretty easy, is 3 times 0 plus 3 divided by 0 plus 2, which is 9/2, which is just 4.5. So that goes up to 4.5, so that makes me cross right there on the y-axis. So what that means is that I know here, because past this vertical asymptote I have no zeros, that means I'm definitely up in positive territory here. And so as I go through here, I know that basically I've got to do something like that, right? I got to go and approach that vertical asymptote on the positive infinity side. And then from there, I need to go and approach the horizontal asymptote as x gets big. Let's keep in mind, though, remember that at x equals 3, we've got to place a hole. So to know precisely where to place that hole, what we should do is plug in 3 into this formula, right? We know you can't plug 3 into the original, but if we plug it in here, that'll essentially tell us if there wasn't a hole there, what should be there? What y value should we be at? So I'm just going to, for my hole here, I'm going to say 3 times 3 plus 3 divided by 3 plus 2. Okay, so what's that? That's 27. Excuse me, not 27, 18 over 5. So, what is that? That's 3.6. So here's 3.6. So that means this is about where the graph would have been. So that's exactly where I'm going to place my hole. Okay. There we go. And so I then can use that kind of as a place marker. And then I just let my graph approach the horizontal asymptote as I go there. So the last task here is we have this vertical asymptote. We know we're positive just to the right of it. So that means just to the left of it we should be negative because of the fact that this factor it came from is just to the first power. And so I definitely know that from this 0 I've got to dive down to negative infinity. Again, remember that you can plug in an x value in here and confirm that you should get a negative there. And then up above the 0, we should definitely be approaching our horizontal asymptote. Put a little arrow there. Okay. So that in the long run, we know that that's what's happening. Okay. Now, what I want to do real quick here is give a little shortcut for this horizontal asymptote business. So if you look back at these previous two examples, down here, we did this process of multiplying by 1 over x squared on top and bottom, and basically convincing ourselves that as x got big, all these terms went to 0 and saw what was left over, right? We did the same thing back in example 1, right here. Okay. Now, if we really analyze what happened here, when we did this, we ended up with 0, y equals 0, because when this term that we're multiplying by in the denominator is bigger than the terms up on top, basically all your top terms go to 0 when you let x get big. But in example 2, we did that, but the terms had the same degree. And so basically one of the terms survived up here. And so both this one and this coefficient survived. So we can kind of put all this together here into some rules. So first of all, if the degree of the top polynomial is less than the degree of the bottom polynomial, then the horizontal asymptote will always be y equals 0. If the degree of the top polynomial is the same as the degree of the bottom polynomial, then what you'll get is basically a term on top and on bottom surviving. And it'll always just simply be the coefficient for the highest degree top term and the coefficient for the highest degree bottom term surviving in top and bottom. And so you'll always just get this fraction a over b. So going back to our previous example real quick, I could have just looked at this original function and said, because the highest degree term on top and bottom are the same, and since the one on top is a 3 and the one on bottom is a 1, I could have immediately said that the horizontal asymptote is 3 over 1, right? So I could have told it just from there. So you can feel welcome to use that analysis. I don't necessarily need to see all this work down here, as long as you can kind of remember that rule and have a good understanding of why it's true. All right, so let's take a look at another example here. So we've got, first of all, some zeros that we want to find, and they're easy to find because it's already factored for us, right? I see no cancellation, so maybe a little note here for no holes. But for my zeros, we've got 2x plus 5 equals 0. So 2x equals negative 5, and x is equal to negative 5 halves. And also x minus 1 equals 0, and x equals 1. So those are our zeros for the function. Then we, of course, have our vertical asymptotes as well. Here we have x minus 6 equals 0, so x equals 6. and x minus 2 equals 0, and x equals 2. So those are our vertical asymptotes. So now let's do horizontal asymptotes the easy way. Okay. Now in this case, it's already factored for us, so it's actually a little more challenging to see what the highest degree term looks like. So we could just FOIL both of these out to see for sure, but let's also understand that when you do FOIL them out, it's the first times the first in both cases that are going to produce the highest degree term. So I'm just going to be lazy here, and I'm going to say this function we're looking at is 2x squared plus stuff on top and x squared plus stuff on bottom, so that I can really just see, okay, here's my highest degree terms. They are all that matter. So that means my horizontal asymptote, as the previous page said, is just the coefficient of 2 over the, in this case, coefficient of 1 on bottom. So y equals 2 is my horizontal asymptote. All right, so now we're kind of getting somewhere. We kind of have an idea of, I think, what our spacing should be. So my last vertical asymptote's at 6, so I need to fit more than 6 tick marks in here. So here we are, here's 6, so I'm going to put my vertical asymptote right there. And then I also have a vertical asymptote at 2. And our horizontal asymptote at y equals 2. Okay. And then we've got our zeros at x is equal to 1, so here's one right here. And x is equal to negative 5 halves, so that's negative 2.5. So negative 1, 2, 3. So negative 2.5 puts me right about there. Okay. All right, so now we got to make some sense out of this. Let's go ahead and find our y-intercept. That always seems to help us. So my y-intercept is when I have x equal to 0. And so if I plug zeros in for all those x's, I end up with 5 times negative 1 divided by negative 6 times negative 2, which simplifies to negative 5/12. And the real important part here is that it's negative. So that means that, as I put a few tick marks here, it's only right about there. But understand what that does tell me is it tells me that between these two zeros, my graph is negative, but it probably doesn't dip down very far. So definitely I know that I'm doing, something like this between these two zeros. Now, after this 0, I've got to be positive, right? And so this one is going to have to approach my vertical asymptote in that way. And then as my x gets more and more negative, and I'm going from negative and crossing a 0, it's going to have to be positive. I know I'm going to have to, approach my horizontal asymptote. So I know it's got to look something like that. And again, in between these asymptotes, there's no zeros, so I'm either all positive or all negative. Now, it's not probably a terrible idea to go ahead and plug in a value here, even though you can probably surmise that it's negative based upon you kind of switching from positive to negative. But then that'll give you an idea of how low to go, essentially. So if I plug in a 4, which would be right in the middle there, let's see what that gives me. So 2 times 4, so that's a 13, times a 3, and then a negative 2 times a 2. So that's 39 divided by negative 4. So that's close to negative 10, right? So this is kind of nice just to get a sense of how low to put this. So the answer is quite a bit lower. So this is quite a ways down here. And so basically, and then we know we've got to approach the vertical asymptotes, and I'm not going to cross the x-axis again because I don't see zeros there. So the only way to do that is to be heading down to negative infinity in both cases. All right. And similarly over here, might not be a bad idea to go ahead and plug in 7, right? R of 7. So if you plug 7 in for x, you get 19. And let's see, times 6 divided by 1 times 5. And I don't know, 19 times 6. Oops, sorry about that. 19 times 6 here is going to be 114 over 5. So that is pretty high up there. So I don't know, 20 something, right? 5 goes in there 22.8 times, I think. So it's way up there, right? So this one's going to be coming from way, way up here. But then in the long run, right, we've got our horizontal asymptote. It's got to settle down and approach that horizontal asymptote as x gets big. All right, so our last example here is going to really just kind of turn this around a little bit. So here I'm going to be given a graph and asked to come up with the function that it has to go with. So on the one hand, we can right away identify important features, right? Vertical asymptotes are at x equals negative 3 and x equals 2. We can see that our horizontal asymptote is y equals 0. And we can see that we have a 0 at x equals 1. And then we can also see that we have a y-intercept at negative 1. So 0, negative 1. So let's set about constructing our function. So the way I'm going to do this is I'm going to say we're going to make r of x. I'm going to put a constant out front first. The reason I'm going to put a constant out front is I realize that things like zeros and vertical asymptotes don't change locations based on just multiplying by a constant, right? But what the constant will do is allow us to have control over what our y-intercept is. So we'll see how that works in a moment. All right, so we'll do this. So we have a 0 at x equals 1, so that means I've got to put the factor x minus 1 in the numerator. Then I've got a denominator that has to have x plus 3 and x minus 2. Those both have to show up in order to have vertical asymptotes in those spots. And then if I have this, do I have a horizontal asymptote of y equals 0? The answer is yes, because the degree of the top is 1 and the degree of the bottom will be 2. And so we'll definitely have that horizontal asymptote of y equals 0. Okay, so the only other thing that we should pay attention to, and this is really kind of a tricky thing, is that notice that the graph stays positive from the left side to the right side of this vertical asymptote. Okay, stays positive from the left to the right of this vertical asymptote. But what we know is when we look at x minus 2, if you plug in the number 1, this factor is negative. If you plug in the number 3, the factor is positive. So if the factor switches signs, shouldn't the entire graph switch signs? So as written, that's true. That's what should happen. But there is something that we can do to make it so that on either side of a vertical asymptote, the signs don't switch. And that would be if we stuck a square on the x minus 2. Because what that will do for us is whatever sign this had, it's going to turn positive after it's squared. And that's going to happen regardless of if you're on the left or the right side. So sticking that square on there is really necessary. This is a little tricky thing. You might need to kind of think about why this has to be there a little bit. Kind of think that through. And what I would say is in your homework, watch out for that one. That one's there's one kind of lurking in there where you've got to think about that. But once we've determined that, we've got our rational function structure all set up, then we can figure out what this a is by using our knowledge of the y-intercept. So when we plug in 0 for x, we know that we should get -1 as the answer. So -1 should equal a times -1 over, and so that'll be 3 times 4 is 12. And I'm kind of running out of space here, but when I multiply both sides by -12 over 1, we get 12 is our a value. So to kind of wrap all this up, our rational function is 12 times x minus 1 divided by x plus 3 times x minus 2 squared. Or if you prefer, you might want to put the 12 up there in the numerator. Either one of these is correct, but you might see the answer written this way as well. In this example, we're going to go ahead and take a look at finding an equation for this one. And in the last example, we had this idea that we can identify vertical asymptotes, we can identify zeros, and build the main structure of our function that way. But understand that we also need to look at any constants that might be involved. So, I can see here, first of all, if I start to write this out. All right, we have x equals 5 and x equals -1 as vertical asymptotes. So that would have to mean that x plus 1 and x minus 5 are factors in the denominator of this function. We can also see that we have zeros here and here, so x equals 3 and x equals 0. So that tells me that I have factors of x and x minus 3 on top. Now I also know that if I put a constant out front here, call it a, that this constant will not change the fact that I have zeros where I have them and have vertical asymptotes where I have them. Now, one way to find this constant, as we've seen, is to plug in a point that is obviously on the graph and use that to solve for a. The problem is the only points that are obvious are these zeros here, which wouldn't do us much good in terms of finding a, because it just zeros all that out. So what we want to do instead is look at the one feature we haven't considered yet, which is the horizontal asymptote. And we have a horizontal asymptote at y is equal to -2. Now remember, in general, you're going to have horizontal asymptotes at things other than 0 when you have a function that looks like this, where the degree of the top and bottom are the same. And when that happens, your horizontal asymptote is always y equals a over b. So just the coefficients in front of the highest degree terms. So what that means, if I distribute out on top there, that would be x squared minus 3x. And down on bottom, it would be x squared minus 4x minus 5. But what do we need? We need a over b to be equal to -2. Or another way of putting it is, let's let a be -2 over 1. And that way, we will make it so that the coefficient in front of the x squared is -2. The coefficient in front of the x squared on bottom is 1. And so we could leave it like this if we want. I suppose that would be okay. We could distribute it through as well. -2x squared plus 6x over x squared minus 4x minus 5. That would be fine as well. But this would be our rational equation for this graph. And by the way, it would be totally fine too to just leave it all factored. If you figured out that a should be -2, you could also just write it like this. All right, so let's take a look at this one here. And right away, I want you to notice a difference between this problem and the ones you've done so far. We've talked a lot about horizontal asymptotes, and remember the rule we gave is that if the degree of the top polynomial is smaller than the degree of the bottom, then your horizontal asymptote is at 0. If the degree of the top and bottom are the same, then you take the ratio of the coefficients in front of the leading terms, right? That's what we did here, right? 2 over 1 was the horizontal asymptote. Okay, but what happens when we end up with the degree on top being higher than the degree on the bottom? The answer is we go back to a concept we've already learned, which is long division. And the reason that we're going to do long division is because it'll be a way for us to re-express the way this function looks. Okay, and maybe that'll help us to kind of understand how this thing is going to look in a different way. So remember with polynomial long division, right? If one of the terms is missing, I want to go ahead and write it in there as a placeholder, so 0x. And then we're saying, what times x squared gives me -x cubed? And the answer to that is x, right? Or -x, excuse me. So -x times x squared is -x cubed. -x times -2x is plus 2x squared. Then we subtract, and so we end up with 4x squared as a remainder. And then we just go ahead and drop these down, plus 0x minus 5. Play the same game again. Okay, I would need to multiply by +4. All right, so we end up with 8x minus 5. Okay, so what does all this mean again? It means that this function up here is also equal to, let me write it actually down here, r of x also could be written as -x plus 4 plus 8x minus 5 over x squared minus 2x, right? So this is the remainder out of x squared minus 2x, right? Think of like when you're writing an improper fraction as a mixed number, right? You're taking the remainder over your denominator, or what you're dividing by. So this is the new function. Now, let's remember that as x goes to plus or minus infinity, then the bottom here is going to get to infinity or negative infinity a lot faster, right, than the top because of the square down here, right? So when the degree on bottom is small or bigger than the degree on top, then everything goes to 0. So this goes to 0 when that happens. Then what we say is r of x looks like this part right here that's just left over. It looks like y equals -x plus 4. Okay, so what is happening here is that this answer, this quotient that we got, is taking the place of our horizontal asymptote. Because it has a variable in it, though, it's not horizontal. It's what we'd call a slant asymptote, or sometimes you hear it referred to as an oblique asymptote. All right, so here's what's going on. I'm going to go ahead and graph this before doing any of the rest of the function. And let me go ahead and put some tick marks in here. So we'll go ahead and let's do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6. Now we can graph this, right? Y equals negative x plus 4 means that I have a y-intercept of 4 and a slope of negative 1. So down 1 over 1, down 1 over 1. Right? We quickly get a nice picture of what this thing looks like. So this is an asymptote now, just like our horizontal asymptotes before, right? It's just that when the degree of the top is larger, we need to do polynomial long division. Now, before we graph anything else, okay, let's go ahead and put this in our calculator, so we can make some sense out of what it means to have a slant asymptote. So pulling up my calculator here, we'll go ahead and type in, we've got negative x cubed minus 6x squared minus 5 on top, and we're dividing that by x squared minus 2x. All right. Now, as I hit graph here, you can see all sorts of stuff occurring. Let's see here. Oh, I think I typed something in wrong. Let's see. That doesn't look like I expected it to look. So we have negative x. Oh, plus 6x squared. That's why. All right, now let's try it. Ah, that looks better. Okay, so all sorts of stuff going on, and we're going to figure out how we know that all this looks the way it does in a moment. But first, let's zoom out a little bit. So if I zoom out, it looks like that. If I zoom out again, it looks like that. Let me zoom out one more time. Look at that. On that third zoom out, I can't even tell that anything different is going on here besides the fact that I just have this negatively sloped line. So what you're looking at right now is essentially the line y equals negative x plus 4, right? So what we're saying is, in the long run, this graph basically just looks like y equals negative x plus 4, okay? And so that's why that's our slant asymptote. All right, but let's go back and fill in all the rest of the details here. So going back up, okay. First off, let's take a look at the bottom. Let's look at vertical asymptotes. So vertical asymptotes are when we set the denominator equal to 0, right? So go ahead and factor there. So we get x equals 0 and x equals 2 are vertical asymptotes, okay? All right, so we can go ahead and fill that in. I guess I'm not going to put one, or I'm not going to draw it in at 0, but I can definitely draw it in here at 2. All right. Now let's take a look at zeros. Okay, now this is a little bit tricky. What this is actually going to require of us is to remember some of our skills from working with polynomials. So we want to set negative x cubed plus 6x squared minus 5 equal to 0. All right, and so remember, the way we start a problem like this is we go to our calculator and see if we can find a nice one. So let's type in the top of our function. So negative x cubed plus 6x squared minus 5. Go ahead and graph that. Oh, that's right, we had it zoomed out from before, so I'll go back to zoom standard. Okay, and I'm thinking my best bet is this one right here. It looks like that's really close. That's pretty much going right through x equals 1. Let's just verify that by finding that 0. So we get to the left, get to the right. So this is just like one of those polynomial problems where I'm trying to find zeros. So I see x equals 1 as a 0, right? So that's one of them. So that's good. X equals 1. And then, of course, what do we do from there? We do synthetic division, right? So we'd have -1 as the coefficient for x cubed, 6, and then we put a placeholder because there's no x term, and then -5. All right, so we've got -1, -1, 5. Okay, so what we're left with here is we've got x minus 1 times -x squared plus 5x plus 5, right, is equal to 0. All right, but now that we've got a quadratic, we can, just use the quadratic formula at this point. Okay, so, on the graph here, I'll go ahead and put in x equals 1, right? So we got a point right there. All right, but let's find these other two. So x equals -5 plus or minus the square root 5 squared minus 4 times -1 times 5, all divided by 2 times -1. So -5 plus or minus, and what do we get there? When we simplify all that, we get 45 in here, all over -2. Now I kind of like to break these up, like I've said before, so I'm going to put -5 over -2, so that's +5 over 2, plus the square root of 45 over 2, or 5 over 2 minus the square root of 45 over 2. All right, so, and then if I put x equals 1 here, those are my 3 zeros. Okay, now of course I need to know about where these things should go on the graph, so let's just understand that we punch both of these into the calculator and get an approximation. So on this one I get 5.85, and on the other one I get -0.85. So going back over here, -0.85 is just inside of -1. 5.85, 1, 2, 3, 4, 5.85, so it puts me right about there. Okay, and so now I go ahead and I try to work this out. I know that as I go toward -infinity, I've got to approach the slant asymptote. So that means I know that I've got to do something like this. And then as I get close to x equals 0, I've got to approach the vertical asymptote. So this has to then go through here on this side of the 0. Over here, again, as x gets really big, I've got to approach this asymptote. So that means this one's got to be down here in the negative. And then this one has to approach that vertical asymptote, so it's got to look like that. Now, lastly here, you don't really have anything concrete at this point to be able to determine whether it's positive on this side or positive on that side. So this is where you just got to plug in something, like plug in x equals 1/2 or something like that. And if you plug in x equals 1/2, you're going to get a positive number. And then if you plug in like 1.5, which would be right here, you're going to get a negative number, so then you're going to get something like this. So this is what this thing looks like on this smaller scale, but remember, if we zoom out, it looks just like this line, y equals -x plus 4.